Okay. So maybe I will start by reminding you what we were talking about in the previous week. And we were talking about inductors. So the inductor is a circuit element, what it does. So here's the thing. We had our circuit symbol for the inductor. And what was the defining relation for an inductor? How did we relate the current in the inductor to the voltage across the inductor? We said for the current positive entering in the positive terminal, what I designate as the positive terminal, the voltage across the inductor is proportional to the current across the inductor. I mean, this is another way to, if you want to see it in another way, think of it like this, L times di dt, which you can also say is the flux. So this is another statement of Faraday's law. All right? Good. But now, let me talk about one more thing. L di dt. Now, what is the power going into any circuit element at any time? Power is always V times I, right? So the power going into an inductor is going to be, I'm just going to use the expression for V, L di dt times I. Now a simple trick. I'm going to write this combination as follows. What is the derivative of I square? Time derivative of I square. 2 times I times di dt, right? So I can maybe write this as 1 over 2 d by dt L I square, or d by dt of 1/2 L I square, right? So the power is the time derivative of something. This combination 1/2 L I square. What was our definition of power? It was energy transferred or dissipated or stored per unit time. So what should this be? This combination is going to be the potential energy stored in a inductor. Okay, so it's going to be 1/2 L I square. This is the potential energy stored in an inductor. Maybe we have learned a very similar formula for capacitors. Do you remember what it was? The energy stored in a capacitor was 1 over 2 C V squared, right? So these are analog relations. How did the capacitor store energy? It created an electric field in a limited region of space, and we said creating an electric field created an energy density 1/2 epsilon 0 E square So there must be a similar law, similar rule for magnetic field. Creating magnetic field in any region of space must be storing energy in that region. Okay, I'm not going to do the calculation. I'll just give you the result. I'll tell you that UB is going to be 1/2 mu 0 B square. This is going to be the energy density of the magnetic field. So we have learned about three kinds of circuit elements. Well, we have also learned the ideal battery, so maybe 4 kinds if you want. We have the resistor, we have the capacitor, and we have the inductor. Now the resistor was fundamentally different from the capacitor and the inductor. Why? Because actually what it does is it does not store any kind of energy, right? It takes electrical energy and converts it into heat or light or whatever else, maybe sound even. But the relation was V was R times I, but this is dissipative, which means it turns usable energy into unusable form of energy like heat. It dissipates energy. It's like friction. How about the capacitor though? The capacitor, our fundamental relation was that I was C dV dt, and this is not dissipative. This is a way to store energy, and the energy stored, we sometimes call it U, we sometimes call it E, is 1/2 C V squared. Similarly, for the inductor, my fundamental relation is V is L di dt, and again stores energy. And now my UL will be 1/2 L I squared. Okay? So the energy you pump into an inductor does not go away, it's not turned into heat. Right? Now we've solved one example circuit. Recall, we solved the following circuit, the RL circuit, right? When we closed the switch at time t equals to 0, what did the current through this system look like? The current through this system did not jump immediately from 0 to its final value, which is going to be V over R, but it actually reached that final value slowly as an exponential. Okay? And what was the time constant for the circuit? Time constant was L over R. Alright? So the larger my inductor is, the slower I will actually reach my final current. Okay? Now, today I want to do something else, another kind of circuit. So this is called the RL circuit. Let's look at the LC circuit. So here's what I'll do. I will take a capacitor and I'll take an inductor. It has a capacitance C and this has inductance L. And at time t equals to 0, I'll say that the capacitor is charged with charge Q0. And at time t equals to 0, I will close the switch. What I would like to find out is what is the current in my circuit as a function of time. And now you immediately see that this circuit is quite different from the RC circuit or the RL circuit we have solved. Why? Because there is no resistance, and when I actually remove resistance from the circuit, there is no way to dissipate energy. Whatever initial energy I had in my system will be stored forever here. Obviously, this is an ideal model. Anytime you have a real circuit, you have wires, those wires will have resistance. But let's say that it's really this resistance is very small. So my initial energy will be 1/2 C V square, or Q0 square over C, will be conserved. Now, when I close the circuit, would it be possible for the current to flow immediately? No. Anytime you have an inductor in the circuit, inductor resists a sudden change in current, so the current must start slowly. Similarly, can the voltage across a capacitor jump? No, it cannot. Anytime you try to change the voltage across a capacitor, it gives out a lot of current, so that must also change slowly. So let's try to write down the equation that actually tells us how the current here behaves. Okay. First, what is the potential across the resistor? Well, the potential across the resistor is obviously, by definition, L times di dt. Good. How about the potential across the capacitor? Well, it's Q of t divided by C. Now, here's the thing though. What is I of t? I of t, where is this current coming from? There is no voltage source, there is no source. It's coming from the initial stored charge on my capacitor. So I of t is dq dt, isn't it? Well, let's be very careful. If I is positive, plus charges are going away from my capacitor. So maybe it should be minus dq dt. That makes more sense. If I have positive current, my charge is going down. Okay. So now I have two equations here, but clearly voltage across the capacitor here is equal to voltage across the inductor, right? So here I have two equations. First one tells me that L di dt is Q of t divided by C, and the second one tells me what I call I is nothing other than dq dt with a minus sign. Now I can combine these equations very easily. What is di dt? Minus the second derivative of q, right? Right, just take a derivative of this equation. And now I can feed it back to the other equation. I can say minus L times d square q dt square is q divided by c. Or maybe I can write this nicely. Once again, I have the opportunity to scare you. I can try to make you give up the course in the last 2 weeks. I can say, hey, this is a differential equation, and in 2 years' time you will have a horribly hard course in differential equations. But really, I mean, look at the equation. It can't be that scary. It says, I have a function, I take 2 derivatives of it, I get back the same function with a minus sign in front. Now, I know that exponential function, e to whatever you have, when I take one derivative, gives me the same function. So if I take 2 derivatives, it will give me back the same function, but it will always have a positive coefficient. So what happens when I have a negative coefficient? Do you know any function which has a negative coefficient when I take 2 derivatives? Sine or cosine. Okay, that's it. that's the way to solve our differential equation. Okay. Only two functions can satisfy this. Either cosine omega t or sine omega t. Okay. Now, why do you need that nice course on differential equations? Because when you take that course, you will actually prove that when I have a second order differential equation, which means a second derivative is the highest derivative involved, if I find two solutions, that's enough. There is not a third solution. You will prove that these two solutions are enough. All right? I will not do that. I'll just say this is the case. Okay? So I'm saying the solution to that equation must be something like the following. Q of t must be some a times cosine omega t plus some b times sine omega t. Let me take the first derivative of that. I'll have minus omega a sine omega t plus omega b cosine omega t. And the second derivative, minus omega square a cosine omega t minus omega square b sine omega t. Or if I write it in terms of the first equation, minus omega square times hey, this is exactly the equation I want to solve. Compare it with the equation I want to solve. Minus 1 over LC Q of t. So what do I see? I see that the oscillation frequency of this circuit is, by comparing, omega square is 1 over LC. So omega is 1 over square root of LC. Now I'm using capital Greek letter omega. I think your book uses omega 0. That's the small case Greek omega. So do not be confused by the notation. All right? What does that tell me? How do I find? I have just found the frequency. I need to calculate A and B. Let's calculate that. So I said Q of t will be A cosine t over square root of LC plus B sine square root of LC. What is the value of Q at time t equals to 0? We said it's Q0. So let's plug t equals to 0 to my equation. What's cosine 0? It's 1. What's sine 0? 0. So A must be equal to Q0. That's great. A we found as Q0. Now I'll do the following. I of t we said was minus dq dt. So if I take a derivative, it's going to be minus 1 over square root of LC A sine t over square root of LC plus B over square root of LC cosine t over square root of LC. Now, what is the current at time t equals to 0? Well, before the switch was closed, it was 0. When I close the switch, can it change? No, it cannot, because there is an inductor there. The inductor resists sudden jump in the current. Okay, the current right after I close the switch must be equal to what it was just before the closing. So it must be 0. So I'm just plugging in 0 here. when I plug in 0, sine 0 is 0. This is going to be b over square root of LC. So apparently b itself is 0. Oh, that's great. So now I've actually found what Q of t is. A is Q0 cosine t square root of LC. Now that I'm here, I can also write the current, which is just going to be minus d by dt of Q. So it's going to be Q0 divided by square root of LC sine t over square root of LC. So what does this circuit do if I plot let's say the charge as a function of time? It's a simple oscillating cosine. It starts at the value of Q0 and does all these nice oscillations. Okay. And when does cosine repeat itself? When the what's inside is equal to 2 pi, right? So what's the period? The period is going to be 2 pi times square root of LC, okay? Because the frequency is omega is 1 over square root of LC. The period is 2 pi over frequency, so it's 2 pi times square root of LC. Now, how about the current? If I plot the current on the same graph. It's going to be a sine, and it will actually be something like this. This is going to be I of t. So what do I see in the circuit? Let's draw different situations here. At exactly the start, I have Q0 charge here and 0 current through the circuit. All my energy is stored in the capacitor. If I wait quarter of a cycle, if I'm at that point, at this point, what's the charge on the capacitor? Charge on the capacitor is 0. How about the current though? Current is at its maximum value, which is apparently Q0 divided by square root of LC. Now, what happens in the next point? Here, again current is 0, but charge is minus Q0. So the polarity of the capacitor has reversed. And then I wait for some more time. If I come to this point, here, again, Q is going to be 0, but now current is flowing in the other direction. So we have this current flowing one way, becoming maximum, then stopping, then it's going the other way. Or if I look at the charge, it's positive Q0, it goes to 0, it becomes negative Q0, and it comes back. Okay, so these are called LC oscillations. Okay, now Let me rewrite. I found Q of t is 1/2, not 1/2, Q0 cosine t over square root of LC, and I find I of t as Q0 over square root of LC sine t over square root of LC. What is the energy stored at any time in the capacitor? The energy stored at any time in the capacitor is 1/2 Q of t squared divided by C. What's the energy stored anytime in the inductor? It's going to be 1/2 L I of t squared. So let's calculate these two quantities. This is going to be 1/2 1 over C Q0 square cosine square t over square root of LC. And this is going to be 1/2 L Q0 squared over LC sine square t over square root of LC. What's the sum of the energy stored in the capacitor and in the inductor? I'm just going to sum these two up. 1/2 Q0 square over C, and here L's cancelled. Cosine square T over LC. Hey, look at the other term. It's going to be, have the same coefficient, sine square T over LC. So when I add cosine square theta plus sine square theta, what do I get? 1. Well, it's great. The total energy in my circuit is conserved. What happens is that initially all the energy was stored as electric field inside the capacitor. At the quarter point of my oscillation, there is no electric field inside the capacitor. All my energy is stored as magnetic field in the inductor. Okay? So I have these oscillations. And if you want to think about it, maybe you can think of the capacitor as some sort of potential energy, the electric field as some sort of potential energy, and the magnetic field as some sort of kinetic energy. Okay? You can just do the reverse, but nonetheless, we're solving the same equations. This is pretty much like any other oscillations you have seen in Physics 101. Right? Good. Now, is there a question? No? You should ask questions. I think this is fascinating. This is really nice. Now, here's the thing. How do you measure time? What are the tools for measuring time? Let's say people, let's not talk about today's fascinating technology. I mean, I measure time by looking at my cell phone. This is not the answer I'm looking for. Okay. If I was a Ottoman Pasha in 18th century, I will go to, I don't know, Smyrna, Izmir, and I want to keep time. What do? I need a pendulum clock, right? If I have a lot of money, I would make a clock tower with a huge pendulum. How do I measure time? I look at how many times my pendulum has oscillated. What will be the accuracy of my measurement of time? Well, I can count. I'm counting how many oscillations my pendulum does. So my accuracy will be controlled by the pretty much proportional to the period of my oscillation. Okay. So you cannot reasonably measure 100th of the oscillation of a pendulum, right? Has it moved 100th of the way? Right. Now, how can we make this more? How can we make time measurement more precise? We need oscillators which are very stable, but they are also doing this motion oscillation at higher frequency, at very high frequency. Right? And now, once people realize that they can actually get reliable LC oscillators, that gave us a better control. It gave us a better way of making clocks. Okay. If you have a nice L and a nice C, you combine them together. For example, if you go to the lab, get a 100 microfarad capacitor, tie it to a 1 millihenry inductor, what would be the frequency of oscillations, or what would be the period of the oscillation of this circuit? Well, the period we have found is 2 pi times square root of L C. So the period will be 2 pi times 100 microfarads is 10 to minus 4. 1 millihenry is 10 to minus 6. So let me make it 10 millihenry. Okay. Or 0.1 millihenry. I like this better. So it's going to be 10 to minus 4 again, right? So what did this give me? 2 pi 10 to minus 4 seconds. So this is going to be around a little bit less than 1 millisecond. Okay. So you could make a 1 millisecond oscillator, a reliable oscillator, in the lab without much effort. I mean, you're just putting two things together. That's not too bad. Of course, the problem here is that clearly we have made a big assumption here. Just like when we were talking about pendulums, we have neglected air resistance, any other kinds of resistance. Here, we are making these things out of wires, and we are saying there is no resistance in the wires. So let's actually figure out what happens if I have some resistance R, L, and C in the system. What will happen in the presence of the resistance? So let's study the RLC circuit. Now, the thing is, let me first write down the central equation that we need to solve here. And after that, we will actually figure out, I will not go through the solution of the differential equation. I'll tell you what happens. Okay, so let's say that I start with some Q0, t equals to 0 is equal to Q0. And I'd like to find out what happens as a function of time, I of t. Clearly, the way I define things, I of t is dq dt. How about if I write down Kirchhoff's loop law over this circuit? What would be the potential on the inductor? It will be L di dt. Potential across the resistor will be R times I, and potential across the capacitor is, well, Q divided by T. So all of them, I've all given my notation that my loop goes in the same way. So VL plus VR plus VC is 0, the way I wrote things down. What I will have is L times di dt plus R times I plus Q divided by C is 0, but I is dq by dt. So what do I have here? D square by dt square q plus r over L dq dt plus q divided by LC 0. That is going to be my differential equation I need to solve. Now, okay, it's a little bit more tricky. I cannot just inspect this and say, hey, you know, I have a solution right away. But I can easily see two limits here. If my resistance is 0, I exactly get back this cosine solution, because that's the differential equation I solved, right? If I have 0 resistance, d square q dt square was minus 1 over LC q of t. It's exactly the same thing here if I kill the second term. On the other hand, if I have a very large capacitance, and think of what that means, the last term can be ignored, and then this time it's a little bit shaky, but I have what's more or less an RL circuit. Right, it's the equation I solved for the RL circuit. Now, how do I solve this differential equation? It turns out my solution has two distinct regimes. If I have only a very small resistance, for example, I really want to make the best oscillator I can, I get the most expensive gold wires which have very small resistance and build my circuit. If R is small, then I'll see many oscillations. Okay. That is called an underdamped oscillator. Okay. Or, in the other hand, maybe I'm not interested in oscillations that much. I have a big resistance. I'm worried about controlling the current in my system. For large R, the solutions will look like exponentials. Okay? And these are called overdamped oscillators. I think you have heard these terms in Physics 101 as well. Have you? You have, but probably it was the last weeks and you were not paying attention. I'm pretty sure you've heard that. But let's at least discuss what happens in these two limits. Okay. So here is the thing. I am going to do the following. I'll write this term separately. R over L dq dt. Now, if there is no resistance in the circuit, I know what my solution looks like. My solution will oscillate. And will the oscillations ever die down if there is no resistance? No, they will not die down because energy, total energy is conserved. But now, what happens if there is a resistance? Do I expect these oscillations to go on forever? No. Every time I'm running current through the resistor, I'm losing some energy to heat. So I expect the oscillation amplitude to be less with passing time. So this is exactly what happens. Okay. When you introduce this resistor, you sort of have this exponential envelope. So you have e to t over tau kind of behavior. And your oscillations will still happen, but their amplitude will be squeezed by this exponential envelope. You're still oscillating, but your oscillation amplitude is going down, and this is the kind of behavior you actually know about. If I get a pendulum, if you look at the pendulum in our department, that's the Foucault pendulum, there is a feedback system at the centers which gives back the energy it loses at each oscillation. If we turn off the electricity, what you see is there is the oscillation which slowly dies down. Okay. That would be the same in an LC circuit. Okay. So oscillations will die out as a function of time. And here is the thing, what does the general form look like? I will start from Q0. I will again have this cosine omega t kind of behavior, but I will also have e to minus t over tau behavior in my solutions. And omega will not be equal to 1 over square root of LC, which we'll call omega 0. Okay, it will be a more complicated form, and tau on the other hand will be again L over R. The thing is, I think what you just need to understand here is why oscillations die out. And in a moment, in the next hour, we'll talk about what happens if we put in some driving force, some source, so that the energy lost to resistance at each cycle is generated by this extra potential. Okay, so see you in 10 minutes.